The story of the forgotten scientific visionary begins in a world where the boundaries of knowledge seemed firmly established, where the laws of physics were considered complete, and the great thinkers of the age believed they had already mapped the universe. But while the scientific community celebrated its achievements, a quiet, brilliant mind worked in the shadows, questioning everything that experts believed was unshakably true. He was not driven by fame, prestige, or the pursuit of recognition. He was driven by an internal fire that burned for understanding, a relentless desire to uncover the deeper truths hidden beneath the surface of reality. His world was not one of grand lecture halls and crowded audiences. It was one of solitary contemplation, where he scribbled equations by the faint glow of lamplight, whispering to himself ideas that sounded impossible to the world he lived in. In an age dominated by classical physics, where Newton's laws ruled like immutable commandments, this man dared to think differently. While others accepted the universe as a clockwork machine, predictable and absolute, he sensed that something was missing. The more he studied the nature of light, the more he realized that the universe did not behave the way textbooks claimed. Small inconsistencies, overlooked by the scientific community, began to disturb him. These inconsistencies grew into questions, and the questions grew into a new worldview, one that challenged the very structure of space and time. He understood that the foundation of physics was cracking, but the world was not ready to admit that its most cherished scientific beliefs were incomplete. As he gathered data, performed calculations, and examined the patterns emerging from his experiments and theories, he began to see a deeper order in the chaos. He recognized that light behaved in ways that classical mechanics could not explain. He began predicting how motion affected the measurement of time, and how observers moving at different speeds might not agree on events happening at the same moment. These thoughts were revolutionary, even dangerous, suggesting that time itself could stretch or compress depending on motion was equivalent to standing in front of the greatest scientists of the era and declaring that everything they believed about the universe needed to be rewritten. Yet he pressed forward, convinced that truth mattered more than acceptance. He did not have the global stage that Einstein would later command. He did not have institutions ready to promote his ideas or peers eager to support his work. Instead, his theories emerged in relative isolation, shaped by personal struggle and an unshakable belief in ideas that nobody else could yet see. His manuscripts reveal lines of reasoning astonishingly close to what Einstein would publish years later. The idea that the speed of light must remain constant, that simultaneity is not absolute, and that the universe's structure bends under the influence of motion. These predictions were not vague philosophical musings, but precise, mathematically grounded insights that pointed directly toward the revolution that would later be called relativity. The tragedy of his story lies in the timing. He was too early. Scientific paradigms shift slowly, and the world he lived in was wired to resist change. When he presented his ideas to his peers, the reaction was not curiosity but dismissal. Instead of engaging with the depth of his reasoning, they brushed it aside as speculation, misunderstanding the profound implications his work carried. He lacked the charisma or the institutional backing needed to force the world to pay attention, and so his papers circulated quietly, unnoticed by the mainstream scientific currents that dictated which ideas were allowed to flourish. Yet within those overlooked papers lay the spark that would later ignite a revolution. As the years passed, he refined his theories, adding more structure, more clarity, more boldness. He realized that the relationship between speed and time was not a philosophical question, but a measurable physical effect. He predicted consequences that no one had imagined, consequences that would later become fundamental concepts in modern physics. He saw that the structure of the universe was more flexible, more dynamic, more interconnected than anyone around him believed. To him, the cosmos was not a simple stage where events unfolded, but a living, breathing fabric shaped by motion, energy, and light. This insight separated him from his generation and placed him decades ahead of them. The scientific community's resistance did not extinguish his passion. It only amplified his resolve. He knew his predictions mattered. He knew they would one day make sense to someone, somewhere, even if he would not live to see it. His life's work became a race against obscurity, a desperate attempt to express truths that only future scientists would have the tools and open-mindedness to fully appreciate. He understood that his ideas were seeds waiting for more fertile soil that would arrive with the next era of physics. Years later, when Einstein published his groundbreaking work, the scientific world erupted in excitement. Newspapers, universities, and scholars hailed Einstein as a visionary, a genius whose mind had uncovered the deepest secrets of nature. But beneath the celebration, hidden from the public eye, were the quiet echoes of the man who had walked the same path long before Einstein ever stepped onto it. The parallels between his predictions and Einstein's discoveries were not merely coincidental. They were signs that he had already cracked open the door to a new understanding of the universe, even if the world refused to follow him through it. But while Einstein became a legend, this earlier scientist remained in the shadows. His contributions were lost in the noise of history, buried beneath the fame of those who came after him. Scholars would later look back and marvel at the accuracy of his predictions, discovering that he had outlined relationships between light and time that closely resembled Einstein's eventual equations. In some cases, his reasoning was so precise, so forward-thinking, that it seemed as though he were glimpsing a scientific future decades ahead of its time. The tragedy is not merely that he was forgotten. The tragedy is that he lived without ever knowing that the world would one day recognize the brilliance he carried. He died believing his ideas had been ignored, unaware that future generations would read his work with awe, acknowledging that he had been among the first to explore the path toward relativity. His life stands as a powerful reminder of how scientific greatness can emerge in unexpected places, of how genius is not always celebrated, and of how the foundations of scientific revolutions often rest on the labor of those who never lived to see their dreams fulfilled. His predictions reshaped the landscape long before Einstein's name became immortal, and understanding his journey forces us to confront a profound truth: the universe does not reveal itself to one person alone. It whispers its secrets to many minds across different times, and sometimes the bravest voices are the ones history almost forgets. As time moved forward and the scientific world gradually opened its eyes to new possibilities, the legacy of the forgotten visionary continued to hide beneath layers of dust, waiting for a moment when someone would rediscover the brilliance he carried. Long after his life had passed, a new generation of physicists began tracing the history of relativity, looking for early thinkers who might have glimpsed pieces of the puzzle before Einstein. What they found was astonishing. Buried within old journals, archived letters, and faded manuscripts were the fingerprints of a mind that had not only anticipated the relativistic worldview, but had done so with startling clarity and confidence. The realization that he had predicted many of Einstein's central ideas cast a long shadow over the narrative of scientific progress and forced historians to reconsider how discoveries are truly made. In his writings, these later researchers found mathematical arguments that pointed directly toward the very concepts that would define 20th century physics. They found expressions describing how light remains consistent regardless of the observer's motion, long before Einstein declared it a universal postulate. They found discussions on the relativity of simultaneity, where he explained that two events viewed as simultaneous from one perspective might not be simultaneous from another, a thought so radical for its time that few could understand its significance. They found reflections on how time itself is not absolute, but elastic, bending to the motion of the observer. Reading his work felt like uncovering a lost chapter of scientific history, one that had been overlooked simply because the world was not ready to listen. What made his insights extraordinary was not just their accuracy, but the courage required to think them at all. In his era, the very notion of questioning absolute time was nearly unthinkable. Newton's worldview was treated like a sacred structure, and anyone who dared to challenge its certainty was dismissed as eccentric or misinformed. Yet he persisted, driven by relentless curiosity and a belief that the universe was more mysterious than his contemporaries imagined. His work shows a kind of intellectual bravery, the willingness to look at the cracks in established theories and follow them, even when the path leads into uncharted territory. It is this courage that allowed him to foresee what Einstein would later become famous for. As historians continued their research, a deeper story emerged, one of isolation, struggle, and the emotional weight of being a thinker ahead of his time. Letters from peers revealed the frustration he faced as his ideas were misunderstood or ignored. Institutions rejected his papers, not because they lacked merit, but because they threatened the comfortable simplicity of established physics. His correspondence reveals long nights spent defending his reasoning, trying to convince others that the universe was far stranger than they believed. Yet no matter how compelling his arguments were, the scientific establishment seemed unwilling to accept ideas that required letting go of centuries of certainty. Behind the equations and theories was a human being wrestling with loneliness. Genius can be a burden when the world is not ready for it. Day after day he continued writing, refining, and revisiting his ideas, unsure whether anyone would ever understand. His commitment to truth became both his guiding light and his source of sorrow. He watched others gain recognition for ideas he had already explored, and though he never expressed bitterness, it shaped his view of the scientific world. He understood that discovery was not just about brilliance, it was about timing, reputation, and social acceptance. Unfortunately for him, he had none of these advantages. When Einstein finally arrived on the scene, he had something this earlier scientist did not: a scientific community that was ready to accept change. The world had begun to question the limits of classical physics. Experiments were revealing anomalies that could not be explained by Newtonian mechanics, and intellectual culture was shifting toward greater openness. Einstein was embraced not only because he was brilliant, but because the world was finally prepared for the truth. The visionary who came before him had walked the same path, but had walked it too early, in darkness rather than daylight. Yet even though he never witnessed the validation of his predictions, his contributions lingered beneath the surface of history. As scientists continued to explore relativity, quantum theory, and the structure of the cosmos, echoes of his early formulations appeared in unexpected places. His influence was subtle but undeniable. For those who took the time to study his work, it became clear that the story of relativity was not the story of a single genius, but of a series of minds who pushed the boundaries of knowledge, each one building upon the faint traces left by those who came before. The rediscovery of his ideas reshaped the way historians understood scientific progress. It revealed that breakthroughs rarely emerge fully formed. They evolve through decades of exploration, frustration, and unnoticed brilliance. In this re-examined narrative, the forgotten visionary became more than a footnote. He became a symbol of the hidden labor behind every celebrated discovery. His life showed that even when the world ignores a groundbreaking idea, the universe has a way of preserving truth until humanity is ready to understand it. As modern physicists revisited his theories, they realized that he had not only anticipated relativity, but had approached it with a style uniquely his own. His reasoning was elegant, his arguments bold, and his conclusions startlingly aligned with what would later become pillars of modern physics. Some even argued that if his ideas had been taken seriously, the revolution of 20th-century physics might have occurred decades earlier. The world might have entered the age of relativity not in the early 1900s, but perhaps in the late 1800s. His forgotten brilliance became a mirror that reflected not only what science gained, but what it lost by failing to listen. Today, his story serves as a powerful lesson about the unseen battles fought by visionary thinkers. Many of the greatest scientific ideas emerge in silence, long before the world is willing to hear them. The forgotten physicist who predicted Einstein's discoveries stands as a timeless reminder that progress does not belong to one person. It is a collective journey guided by countless minds, some celebrated, some marginalized, and some nearly erased from memory. The tragedy of his obscurity is matched only by the beauty of his persistence. He continued working even when recognition seemed impossible. He remained committed even when doubts surrounded him. In the quiet of his study, surrounded by equations that the world would not accept, he found the strength to trust the universe more than the opinions of his peers. He believed that nature's truths were worth pursuing, even if no one else believed in him. As we reflect on his life and his extraordinary predictions, we see more than an overlooked scientist. We see the embodiment of the scientific spirit, the willingness to question, to explore, and to follow evidence wherever it leads. The man who predicted Einstein's discoveries reminds us that the universe does not give its secrets to the loudest voice or the most famous name. It reveals them to those who seek truth with courage, humility, and unwavering dedication. And so his legacy endures, not in the spotlight he never received, but in the quiet recognition of those who have taken the time to rediscover his brilliance. His work lives on in the equations that shape modern physics, in the theories that describe our cosmos, and in the stories told about him. Stories that finally give him the place he deserved all along. Though history nearly forgot him, the truth did not. His predictions became part of the foundation upon which Einstein built, proving that even the most overlooked mind can help reshape humanity's understanding of the universe. In the early years of modern science, when great discoveries were beginning to reshape humanity's understanding of the universe, one man quietly developed ideas so daring that they seemed almost impossible for his time. He observed the world with an intensity that set him apart from his peers, seeing patterns and contradictions others overlooked. While the scientific community focused on perfecting old theories, he was already diving into concepts that stretched far beyond the limits of traditional thinking. His fascination with light, motion, and time consumed him, pushing him to question everything society believed about how the universe functioned. This questioning did not arise from rebellion, but from a deep, honest curiosity that refused to accept inconsistencies. Whenever he found a piece of the puzzle that didn't fit, he followed it relentlessly, even when it led him into territory few dared explore. His early work began with simple observations. Light, he noticed, behaved in miraculous ways. Sometimes it acted like a wave, spreading smoothly across space. Other times it behaved like a particle, striking with precision and strength. These contradictions fascinated him. He believed that if he could understand light fully, he could unlock the deeper laws that governed the universe. Night after night, he filled notebooks with calculations, diagrams, and theoretical sketches, often working long after the world around him had fallen asleep. He imagined beams of light racing across the cosmos, unaffected by the motion of the observer, moving with a constancy that defied classical mechanics. He wondered if the behavior of light could reveal hidden structures within space itself. As he studied the nature of motion, his ideas grew bolder. Classical physics insisted that time flowed equally for everyone, that clocks anywhere in the universe ticked in perfect harmony. But he began to suspect that this notion was flawed. What if time was not fixed? What if it depended on the motion of the observer? What if two people moving at different speeds experienced different versions of the same moment? These thoughts were radical, almost heretical in his era. Yet he could not deny the patterns emerging in his calculations. He saw that events viewed from one frame of reference might appear completely different from another. The universe, he realized, was not the rigid stage scientists believed it to be. It was flexible, fluid, and deeply connected to the speed at which one moved. As these insights grew stronger, he attempted to share them with colleagues, hoping for dialogue, debate, or even criticism that might help refine his theories. But most scientists of his time were resistant. They found his questions unnecessary, even dangerous. Why challenge established laws when those laws had served perfectly well for centuries? Why risk destabilizing scientific order with ideas that felt more like philosophical speculation than testable reality? His attempts to explain the relativity of time and the behavior of light were met with confusion or dismissal. The more he tried to present his work, the more isolated he became. But rather than discouraging him, this isolation pushed him deeper into his research, strengthening his resolve to uncover the truth, whether the world accepted it or not. He continued to examine how light interacted with moving objects, running mental experiments that allowed him to explore extreme conditions no laboratory could recreate. He imagined riders traveling at incredible speeds, observing how their experience of time would change. He pictured clocks on fast, moving trains running slower than those on the ground, even though no one could measure such effects at the time. He visualized light beams chasing after speeding observers, maintaining their velocity regardless of how fast the observer moved. These thought experiments strengthened his belief that the universe operated on rules far more complex and beautiful than anyone yet understood. His predictions were astonishing. Long before any experimental evidence existed, he proposed that the speed of light must remain constant, no matter the motion of the observer. This idea contradicted everything classical mechanics taught. If a person throws a ball while running, the ball's speed increases relative to the ground. Why then, he wondered, should light behave differently? Yet all his reasoning showed that light did not care about the motion of its source. It moved with unwavering consistency, as if it followed a cosmic commandment. To him, this was not just a property of light. It was a hint that the universe obeyed rules deeper than human intuition. Light became his guide into the unseen architecture of reality. Through years of obsessive study, he developed the revolutionary idea that time itself might stretch or compress depending on one's velocity. People moving at incredible speeds would age more slowly than those at rest. Time, he realized, was not a universal river flowing uniformly through the cosmos. It was more like an elastic thread, capable of bending and shifting according to the motion of the observer. In his notebooks, he wrote equations that showed how time dilation would occur, predicting effects that would later be confirmed by advanced atomic clocks and space travel. But in his era, such predictions were too strange to be believed. The resistance he faced from the scientific community only grew stronger as his theories evolved. His colleagues accused him of being a dreamer, an idealist detached from practical science. They insisted that the universe was simple, predictable, and absolute. But he saw complexity where they saw simplicity, possibilities where they saw limitations. The more they tried to silence him, the more determined he became to express his ideas clearly, meticulously, and courageously. His work was not only mathematically bold, it was deeply philosophical. He believed that nature's truths were hidden beneath layers of assumptions passed down through generations. To uncover these truths, one had to question even the most sacred principles. He asked himself simple yet profound questions. What is time? What is motion? What is reality when observed from different perspectives? These questions guided his exploration and gave rise to the early foundations of ideas that would later transform physics forever. Despite the rejection, he never abandoned his pursuit. He continued refining his theories, searching for ways to present them that others might finally understand. He published papers in lesser-known journals, hoping that even if mainstream scientists ignored him, anyone, might recognize the significance of his discoveries. And in these papers lay the roots of concepts that Einstein would later develop into one of the greatest scientific revolutions in history. His predictions about light, motion, and time were not vague philosophical musings. They were precise, logical, and astonishingly accurate. He calculated how objects approaching the speed of light would behave, how frames of reference would shift, and how the universe would appear to someone moving near such extreme velocities. His equations foreshadowed mathematical structures that future physicists would rely on to understand not only relativity, but aspects of quantum mechanics as well. What makes his work remarkable is not only its similarity to Einstein's later theories, but the fact that he reached these conclusions with far fewer tools, less recognition, and no access to the emerging technologies or experimental data that Einstein could rely on. His work was the product of pure thought, a mind exploring the universe with nothing but intellect, imagination, and curiosity as tools. As he continued pushing forward, he became increasingly aware that he might never receive recognition during his lifetime. Yet this realization did not discourage him. Instead, it strengthened his belief that he was working for something larger than himself. He felt that truth, once discovered, carried its own destiny. If the world was not ready to accept it today, then perhaps tomorrow, or decades later, someone would rediscover his writings and finally understand. This first half of the story captures the moment when his ideas reached their peak, when his predictions about the nature of light, motion, and time became too extraordinary to ignore in hindsight. It reveals a man whose mind lived decades ahead of his era, whose ideas crossed into the very territory that Einstein would later illuminate for the world. As the years continued to pass, the man who had quietly unraveled the deeper workings of the universe faced a growing sense of isolation. The scientific world around him marched confidently in the direction of classical certainty, reinforcing the belief that the universe was stable, predictable, and governed by rules that had been accepted for centuries. Yet he continued to see cracks forming in those old ideas. Every new calculation he made, every pattern he studied, revealed a universe far stranger and more dynamic than the one his contemporaries insisted upon. His intuition told him that he was moving toward a profound truth, even if the world seemed determined to ignore him. He refined his theories with a patience that few could match. Each new insight built upon the last, forming a chain of reasoning that grew stronger despite being unseen by the world. He questioned how motion affected not just time, but the way objects interacted with space itself. He suspected that distances could shrink for observers moving at extreme velocities, a realization that contradicted everything known in classical geometry. If the universe behaved differently for observers in motion, then reality itself was not fixed. It changed depending on where you stood and how fast you moved. This idea would later become a cornerstone of modern physics, yet in his time it was dismissed as speculation. He wrote endlessly, filling notebooks with equations that would one day appear familiar to physicists studying relativity. He understood that for the speed of light to remain constant, space and time must work together in a delicate balance. If one changed, the other compensated. He imagined that the universe was not a static container, but a flexible stage capable of bending under the laws of motion. Space could contract, time could dilate, and the division between past, present, and future could shift depending on the motion of the observer. It was a view of the universe that his generation could scarcely comprehend. The more he explored, the more he realized that motion and light created a cosmic dance that shaped everything we experience. He saw that no object could ever surpass the speed of light, not because of mechanical limitations, but because the structure of the universe itself prevented it. As velocities increased, time slowed down, distances shortened, and the energy required to accelerate an object grew infinitely large. These predictions were extraordinary for a man living in an age when understanding of electromagnetism was still in its early stages. Yet through pure thought alone, he anticipated principles that would later become scientifically proven. Despite his brilliance, his life was not easy. Financial difficulties, lack of institutional support, and the constant rejection of his ideas weighed heavily upon him. He often worked in solitude, surrounded only by his papers and the quiet hope that one day his discoveries would matter. Friends and colleagues encouraged him to abandon his radical theories and focus instead on safer, more acceptable lines of research. But he refused, believing that progress in science depended on courage, the courage to challenge old ideas, even when facing overwhelming opposition. He continued to publish his work, sometimes in minor journals that few people read. His ideas rarely attracted attention, and when they did, they were often misunderstood or misinterpreted. Critics dismissed him as someone chasing impossibilities. Yet when historians and physicists would revisit his work decades later, they found that many of his predictions aligned almost perfectly with the theories Einstein would eventually develop. It was as though he had glimpsed the blueprint of the universe long before the world had the tools to understand it. As the 20th century approached, the scientific world finally began to experience the cracks he had identified long ago. Experiments revealed anomalies in the behavior of light and electromagnetism that could not be explained with classical physics. Young scientists began questioning whether Newtonian mechanics could truly describe the universe at high speeds or in extreme conditions. The scientific community became more curious, more open-minded, more willing to explore ideas beyond the comfort of tradition. And in this new atmosphere of questioning, Einstein emerged with a bold vision, a vision that echoed many of the thoughts the earlier scientist had written decades before. When Einstein's work was published, it captured the world's imagination. His ideas were revolutionary, elegant, and backed by mathematical precision that stunned even the most respected physicists. Suddenly, concepts like time dilation, simultaneity, and the constancy of light became central to scientific discussion. Newspapers around the globe hailed Einstein as the mind who had rewritten the laws of physics. Universities embraced his theories. Students studied them with enthusiasm. For the first time in history, the universe was seen not as a rigid machine, but as a dynamic fabric woven together by space and time. But while Einstein became a legend, the man who had predicted many of these ideas long before did not share in the glory. His writings remain tucked away in archives and libraries, read only by the very few who took the time to search through them. Even as scientists began discovering that his earlier work aligned beautifully with relativity, the world remained largely unaware of his contributions. Historians would later describe his situation as one of the greatest missed opportunities in the history of physics. A moment when the scientific world could have advanced decades sooner had it listened to the quiet genius in its midst. Yet in many ways, his legacy is even more powerful because it was not shaped by fame. His pursuit was driven purely by the love of truth. He sought knowledge not for recognition, but because he could not stop thinking about the mysteries of the universe. His mind lived in the future, imagining concepts that would take decades for others to fully accept. He was not limited by the expectations of his era or the assumptions of traditional science. Instead, he followed the trail of logic wherever it led, even when it led him into isolation. His story serves as a profound reminder of how scientific breakthroughs truly unfold. They are not the work of a single genius, but the culmination of many thinkers who contribute pieces of the grand puzzle. Some receive recognition, others are forgotten, but each plays a role in uncovering the truths that shape our understanding of reality. This man, who predicted the core ideas of relativity long before Einstein, stands as a symbol of the invisible foundation upon which scientific revolutions are built. His writings, rediscovered years later, became a testament to the power of intellectual courage. Researchers found detailed descriptions of time dilation, explanations of how observers in motion would measure events differently, and arguments for why the speed of light must remain constant across all frames of reference. These were not vague ideas. They were precise predictions that matched the equations of relativity almost perfectly. Reading his manuscripts felt like stepping into a time machine, witnessing a mind that was living decades ahead of the world around him. As modern physicists began acknowledging his role in shaping the early development of relativity, his place in history slowly grew more significant. He became not a rival to Einstein, but a precursor, someone who lit the early spark that would one day become a scientific explosion. He demonstrated that truth does not always emerge in the spotlight. Sometimes it grows quietly, unnoticed, waiting for the world to catch up. In the end, his story is not defined by the recognition he never received, but by the brilliance he carried. He left behind a legacy of ideas that helped reshape the universe, even if the world didn't realize it at the time. His dedication, his persistence, and his courage to challenge the seemingly unshakable laws of physics reveal what it truly means to be a visionary. He stands as a reminder that greatness does not depend on celebration, but on the willingness to explore the unknown. And as we reflect on his life, we see how the fabric of modern physics is woven with the threads of his forgotten discoveries. The universe he envisioned, one where time bends, light stays constant, and space shifts with motion, is the universe we live in today. His predictions became the foundation upon which future generations built their understanding of reality. Though his name may not be known to many, his ideas continue to echo through every corner of science, shaping the way humanity perceives the cosmos. The transformation of scientific thought is often portrayed as a series of dramatic revolutions, but the truth is more subtle. It unfolds through the long, deliberate construction of ideas that at first appear fragile, almost invisible, yet slowly gather the power to reshape the foundations of knowledge. In this story, that transformation begins with a man who possessed an uncanny ability to perceive the hidden currents flowing beneath the surface of physics. He worked far from the crowds, far from fame, yet his insights seemed to run parallel with the greatest scientific breakthroughs of his era. Even before Einstein's work became celebrated across the world, this man had already been tracing the lines of a deeper truth, a universe not governed by rigid absolutes, but by relationships, motion, and the interplay between the observer and the observed. His contributions were not accidents of intuition. They were the result of relentless observation and a rare willingness to question the most sacred assumptions of classical science. He looked at the world with an intensity that made ordinary details feel like clues. A beam of light passing through fog, a pendulum swinging under moonlit air, the stillness of a quiet morning, these were not just pieces of nature, they were messages. He believed that in the smallest, simplest motions of the universe, the greatest mysteries hid silently in plain sight. This was long before relativity had shaken the world, long before the fabric of time and space had been exposed as dynamic, elastic, and alive. Yet he sensed that the universe could not be as fixed as Newtonian mechanics claimed. Something was incomplete. Something was waiting to be discovered. His early work revolved around a bold conviction that nature reveals itself not through dogma but through contradictions. When a theory fails, it is not an embarrassment, it is an invitation. And so he dedicated himself to searching for the inconsistencies buried within the physics of his time. He studied the behavior of light with a fascination bordering on obsession. Scientists had long believed that light moved through a hypothetical medium called the aether, but he doubted this idea. If the ether existed, he argued, it should create measurable effects. It should resist motion or distort speeds. Yet experiment after experiment suggested otherwise. Light behaved with a stubborn consistency, refusing to change speed regardless of the observer's frame of motion. How, he asked, could a world built on absolute space allow such defiance? This question was radical, even dangerous. It challenged the entire framework of classical physics. But he embraced it fully, knowing that truth often hides where established ideas begin to crack. He began developing mathematical expressions that hinted at something startling, the possibility that measurements of distance and time were not universal. They shifted depending on the observer's state of motion. This idea was nearly unthinkable in the 19th century. Space was space. Time was time. These were believed to be the pillars of the universe, stable and eternal. Yet his calculations whispered otherwise. They suggested a universe that adapted itself to motion, a universe that protected the speed of light as a constant, even if it meant altering the very fabric through which events unfolded. His work did not emerge in isolation. He studied the experiments of his contemporaries, absorbing every result like a detective connecting clues. When the famous Michelson-Morley experiment failed to detect the aether wind, many scientists were confused, even disappointed. But he saw it as confirmation. It aligned perfectly with the mathematical relationships he had uncovered. The universe was trying to tell them something, that the laws of physics required symmetry, that motion could not be detected simply by measuring the speed of light, and that the structure of time and space must adjust itself to preserve this cosmic harmony. He developed transformations, powerful and elegant equations, that described how time and space appeared to contract and dilate for observers in motion relative to one another. These transformations would one day become the mathematical backbone of relativity, but at the time, they were seen only as clever mathematical tricks, tools for explaining experimental anomalies. He insisted that they were more than tools, they were descriptions of reality. But most physicists were reluctant to accept such a dramatic shift. They believed that the transformations were just an adjustment to preserve the illusion of the ether. They could not imagine that time itself might change for different observers. His struggle was the struggle of every visionary thinker. To speak a truth the world is not yet ready to hear. But he did not waver. He continued refining his work, exploring the implications of relative motion, questioning the very foundation on which classical mechanics had been built. He began to see that the universe was far more interconnected than anyone imagined. Time, space, motion, energy, these were not independent categories but interwoven aspects of a single, unified existence. In the quiet hours of his study, he wrote with astonishing clarity, proposing that the equations describing electrical and magnetic fields should remain unchanged for all observers, regardless of their speed. This was a breathtaking idea. It implied that the universe possesses an underlying symmetry, a kind of cosmic fairness, where the laws of nature do not privilege one perspective over another. It was a philosophical breakthrough as much as a scientific one. It transformed the observer from a passive spectator into an integral part of the physical world. The reality a person experiences depends on how they move through space and time. This was a revelation decades ahead of its time. At first, his ideas circulated quietly, often misunderstood, often dismissed. Some appreciated the ingenuity of his equations, but missed the revolutionary implications behind them. Others simply ignored the possibility that nature might operate on principles more subtle and dynamic than the rigid laws they had inherited. Yet he persisted. He refined, rewrote, and recalculated, driven by the belief that truth eventually finds its way into clarity. He believed that science must evolve, not by clinging to old assumptions, but by daring to reimagine the universe. In his analysis of time and motion, he touched on a concept that would later become central to modern physics, the relativity of simultaneity. The idea that two events can appear simultaneous to one observer, but not to another, was deeply counterintuitive. Yet he showed how it emerged naturally from the behavior of light and the transformations he derived. This was a direct challenge to centuries of scientific thought. Simultaneity had always been treated as absolute. Events happened when they happened. But he demonstrated that simultaneity was not universal, that the order of events could depend on one's frame of reference. It was a profound insight, one that anticipated the heart of Einstein's later work. He explored how moving clocks would appear to run slower, how moving lengths would appear shorter. He traced these effects not to illusion, but to the geometry of spacetime itself. His mind worked like a lens, bringing into focus patterns no one else could see. He envisioned a world where velocities combine, not through simple addition, but through a deeper structure governed by the speed of light. His calculations anticipated the breakdown of classical addition of velocities, a cornerstone of modern relativistic physics. All of this was happening years before Einstein published the paper that changed history. This man had already walked the path that Einstein would later illuminate for the world. But he did not seek fame or recognition. His satisfaction came from uncovering truths, from peeling away the layers of misunderstanding that obscured the universe's deeper order. He believed that science belonged not to individuals but to humanity. He believed that ideas were vessels, not monuments. He continued to refine his understanding of motion, energy, and transformation, uncovering relationships that would later become indispensable to the development of relativity and modern physics. His insights were not just predictions, they were frameworks. They provided the mathematical and conceptual scaffolding upon which the next generation of scientists would build their revolutions. He had seen the shape of the future before the world even knew the questions that needed to be asked. The momentum of his work carried him deeper into the heart of nature's hidden structure, revealing layers of meaning that would only be understood years later. He sensed that the universe did not simply allow relative motion, it expressed itself through it. Every movement, every measurement, every observation was woven into a larger tapestry of relationships. What most scientists saw as complications, he saw as clues. He believed that nature was whispering a consistent message, that the laws of physics did not bend for those who tried to impose rigid interpretations. Instead, they revealed themselves only to those who were willing to rethink everything, even the most fundamental definitions of time, space, and motion. His reflections often drifted toward the deeper philosophical meaning of his discoveries. What did it mean for time to flow differently for observers in motion? Was time really a universal river washing over all things equally, or was it something far more nuanced? He imagined two observers traveling at different speeds, each with their own clocks ticking, unaware that their experiences of time diverged with every passing moment. To him, these were not merely abstract ideas, they were realities waiting to be embraced. He realized that the world people experienced was not the world as it truly was, but rather the world as it unfolded within their particular state of motion. This was a profound realization, one that redefined the observer's place in the universe. He turned his attention to motion itself. Classical physics treated motion as something external, something that happened to objects as they traveled through static space and time. But he proposed the opposite. Motion was not an isolated condition, it was a relationship. It defined how one observer perceived another, how one event related to another, how measurements transformed depending on perspective. He imagined a universe where every point of view was valid within its own frame, where no single observer possessed an absolute description of reality. This was not a limitation but a revelation. It meant that the universe was democratic in its laws, offering no special privilege to any one viewpoint. As his ideas evolved, he began to sense a deeper truth, that the rigid separation between space and time was an illusion born from classical thinking. Although he did not articulate the full geometry that would later redefine these concepts, he laid the foundation by exposing the fluid relationship between the two. When he described how time dilates and lengths contract, he was not merely offering corrections to classical formulas. He was revealing hints of a world where time and space were intertwined, responding together to the motions of the observer. This insight would later be recognized as one of the most transformative leaps in scientific history, but for him, it was simply a consequence of nature's consistency. His work often unfolded in solitude. He would sit for hours at a wooden desk, papers scattered, ink staining the edges of his fingers. The world outside continued in its ordinary rhythm, unaware of the conceptual earthquake forming quietly in his mind. He spoke little, preferring to let the mathematics converse with him. He trusted equations more than human opinions. Where others saw paradox, he saw elegance. Where others clung to familiar interpretations, he embraced the uncertainty necessary for progress. His quiet dedication became the catalyst for ideas that would later become monuments of modern physics. Scientific culture of the time was slow to recognize the significance of his contributions. The academic world was rooted firmly in Newtonian principles, and scientists were reluctant to abandon the certainty of laws that had guided them for centuries. Yet he persisted, not with confrontation but with clarity. He continued refining the transformations that bore his name, adjusting the relationships between time, space, and velocity until they formed a coherent structure. These transformations were not just mathematical conveniences. They were blueprints of reality. They captured the delicate choreography nature performs when observers move at high speeds. He considered the role of light with a sense of awe. Light was not simply a phenomenon to be studied. It was a messenger. It conveyed universal principles, refusing to alter its behavior regardless of who observed it. This stubborn constancy of light was the key to everything. If light insisted on maintaining a fixed speed, then the universe had no choice but to adapt itself around that fact. Clocks, rulers, distances, and durations all would shift subtly to ensure that the laws governing light remained unchanged. He saw this not as a complication, but as a sign of deep harmony in nature. The universe was protecting its symmetry, preserving balance across all frames of motion. As he explored the consequences of these ideas, he began to uncover patterns that bordered on the poetic. He realized that the more an object approached the speed of light, the more its experience of time slowed. To a fast-moving observer, time stretched, allowing the universe to unfold leisurely. To a stationary observer, that same traveler appeared bound by a different rhythm. It was as though the universe allowed each observer their own tempo, their own unfolding. This concept would later become a cornerstone of modern physics, transforming the understanding of motion, energy, and causality. But long before it was celebrated, he had already traced its contours. He recognized that energy and motion were deeply connected in ways classical physics had never imagined. Though he did not derive the iconic formula that would later become synonymous with Einstein, his insights paved the path for understanding the intimate relationship between mass and motion. He sensed that energy was not merely a property but a dynamic expression of how objects move through time and space. As velocity increased, the energy required to accelerate an object began to grow disproportionately, hinting at limits imposed by the structure of spacetime itself. These were the seeds of ideas that would later blossom into some of the most profound scientific breakthroughs of the 20th century. In the quiet progression of his work, he confronted a challenge that would shape the future of physics: how to reconcile the laws of electromagnetism with the principles of motion. Many scientists struggled with contradictions arising from classical interpretations. But he approached the problem differently. Instead of forcing old ideas to fit new facts, he allowed the facts to reshape the theoretical landscape. He proposed that the equations governing electric and magnetic fields must remain the same for all observers. A bold declaration that demanded the rethinking of fundamental assumptions. This principle, though underappreciated in his time, became a foundational pillar for the revolution that followed. He saw symmetry everywhere, in the way equations balanced, in the way light behaved, in the way motion transformed perspectives. To him, symmetry was not merely aesthetic, it was the language of nature, and the universe spoke it fluently. His transformations were expressions of that symmetry, revealing how observers in relative motion could all describe the same physical laws without contradiction. This was a profound insight, one that placed him far ahead of his contemporaries. Despite his pioneering work, many of his peers struggled to grasp the radical nature of his ideas. They saw his equations as clever artifacts rather than windows into the universe's true structure. Some believed his insights were mathematical conveniences, never imagining that they described the fabric of reality itself. Yet he never let frustration overshadow his pursuit. He understood that science evolves slowly, that even the most groundbreaking ideas require time to find acceptance. He trusted that the future would understand what the present could not. As the years passed, his work quietly shaped the thinking of others. Young scientists began to explore the implications of his transformations, unaware at times of the depth he had already achieved. His legacy began to take root beneath the surface, influencing minds who would later become giants of the scientific world. Though he did not witness the full recognition of his insights, his contributions became woven into the foundation upon which modern physics was built. The world eventually came to realize that he had not merely explained experimental anomalies. He had predicted the conceptual framework that would redefine reality. He had glimpsed a universe where absolutes dissolved, where motion shaped experience, where time and space fused into a single continuum. His work anticipated the core structure of a revolution that would later bear another man's name, yet his influence radiated quietly through the decades, a reminder that history does not always honor its true pioneers immediately. His journey exemplified the power of intellect unburdened by fame, ambition, or the desire for recognition. He sought only truth, guided by deep curiosity and an unwavering commitment to understanding the hidden order of the cosmos. In doing so, he became one of the few individuals who could see the shape of the future long before the world realized it was changing. He moved through the world with a sense of quiet urgency, as though he carried within him a secret that he had not yet learned how to reveal. The more he studied the mysteries of the physical universe, the more he realized that the truth was not hidden in grand theories, but in the subtle patterns connecting them. His mind worked like a finely tuned instrument, alert to every discrepancy, every anomaly that other scientists overlook. He believed deeply that the future of physics would be shaped not by expanding old ideas, but by dismantling them and letting the deeper structure of reality emerge. This belief became the force that drove him forward, pushing him to challenge centuries of assumptions that had shaped scientific thought. He understood that nature rarely speaks in a single voice. It speaks in echoes, in repetitions, in small deviations that, when viewed with the right perspective, form a message. He noticed those messages everywhere. In the way light refused to behave as expected, in the way electromagnetic laws demanded consistency even when classical theories resisted. He began to see the universe not as a machine of fixed parts, but as a living symmetry, a harmony that extended across time, motion, and perception. Everything was connected. Every law demanded another law to balance it. Every observation reshaped the observer. The more he explored the behavior of light, the more he sensed that the universe was whispering a fundamental truth, that reality could not be defined by absolutes. It must bend, adjust, adapt to preserve a deeper order. He saw this adaptation reflected in the strange resilience of the speed of light, a constant that refused to yield no matter how fast the observer moved. This stubborn consistency seemed to defy the foundations of classical physics, yet it fit perfectly within the transformations he had discovered. To him, this was not a contradiction but a revelation. It meant that the laws of nature were encoded with an internal logic that protected consistency across all frames of motion. He recognized the silent power of symmetry long before it became a guiding principle in modern physics. When he examined the equations describing electric and magnetic fields, he saw something extraordinary. These equations did not care about the observer's motion. They did not adjust themselves based on who was watching. Instead, they held firm, revealing a deeper truth that the universe was built on principles that transcended individual perspectives. This realization guided him to construct a framework in which the laws of nature remained unchanged for all observers. It was a profound shift that placed the observer within the universe, not above it. His work took shape during a time when scientific culture held tightly to old assumptions. The belief in absolute space and absolute time was so deeply ingrained that questioning it felt almost sacrilegious. Yet he questioned it with calm persistence, confident that the truth was worth the discomfort it created. He navigated resistance not with arguments but with clarity, letting the consistency of his equations speak on his behalf. He believed that if nature pointed in a certain direction, then science must follow, regardless of how radical that direction seemed. His insights expanded into a new understanding of motion. He explored how objects moving at high speeds experienced time and space differently from stationary observers. He envisioned clocks that ticked slower as they accelerated, lengths that contracted as objects raced forward. These ideas were not fantasies but natural consequences of the transformations he had meticulously derived. He saw these effects as part of the universe's attempt to maintain harmony, adjusting the flow of time and the structure of space to preserve the laws that governed them. To him, this was not a limitation placed on nature, but a sign of its profound balance. He understood that the universe was not static, it was dynamic, fluid, responsive. The way events unfolded depended not merely on what happened, but on who observed them and how quickly they moved. Simultaneity, once believed to be absolute, dissolved under the weight of his reasoning. He realized that two observers might disagree on whether two events happened at the same time, and both could be correct within their own frames of reference. This was not a contradiction, but a revelation of the relative nature of time. He saw that time was not a universal rhythm, but a personal experience shaped by motion. The more he explored, the more he felt that he was standing at the edge of a new world, a world where space and time were no longer separate entities, but partners in a cosmic dance. Though he did not articulate the full geometry that would later unify them, he sensed their connection. He recognized that every measurement, every observation, every physical law existed within a framework far more flexible and interconnected than classical physics allowed. His work became a bridge between two eras, the age of fixed absolutes and the dawn of relativity. His influence grew quietly, without public acclaim or dramatic recognition. He did not seek fame, nor did he expect to be celebrated. His satisfaction came from the pursuit itself, from uncovering patterns that others had missed, from revealing structures hidden beneath the surface of established theories. He believed that science was a continuum, built not by individuals seeking glory, but by minds willing to question everything. His ideas flowed forward like a river, shaping the thoughts of others long after he had written them down. Though history often remembers the loudest voices, it is the quiet ones who sometimes lay the foundation for revolutions. His work became a silent cornerstone, supporting discoveries that would redefine physics for generations. Later scientists would stand upon this foundation, transforming his insights into complete theories that changed the world. Yet his fingerprints remained on every one of those breakthroughs, a testament to a mind that saw the future long before the world was ready to understand it. What he left behind was more than equations. It was a vision of a universe where motion shapes reality, where observers shape time, where the laws of nature remain beautifully consistent no matter how the world is perceived. He revealed that the universe is not governed by absolutes but by relationships, and in doing so, he opened the door to one of the greatest scientific transformations in history. He stepped into a period where science was standing at a crossroads, torn between the comfort of old certainties and the discomfort of new truths pushing their way into the world. The deeper he ventured into the study of motion, energy, and light, the more he realized that the universe was not built upon rigid foundations. Instead, it was shaped by shifting relationships, subtle transformations, and hidden symmetries that waited patiently for minds daring enough to perceive them. He became one of those rare individuals who not only sensed the direction in which science was moving, but also illuminated the path long before others realized such a path existed. His work, though not wrapped in fame or dramatic announcements, carried a quiet brilliance. In the quiet hours of his study, he would dissect the behavior of light with the precision of a surgeon, uncovering the structure of an intricate organ. He understood that light was more than a mere wave traveling through space. It was a messenger from the universe's deepest laws, revealing truths that contradicted everything classical physics had taken for granted. As he examined experiment after experiment, a pattern began to form, a pattern that pointed to a universe where motion shaped reality itself. He contemplated the way light held its speed constant, refusing to adjust even when observers moved rapidly toward or away from it. This defiant consistency fascinated him. It felt as though light was obeying a rule that stood above all others, a rule that demanded the alteration of space and time, rather than allowing its own behavior to change. He began to understand that this constancy was the universal anchor around which the entire structure of reality revolved. If light would not bend, then everything else must. Clocks must slow, distances must shrink, events must shift, and observers must become part of the fabric they once believed themselves separate from. He recognized the courage required to accept such an idea. It meant abandoning centuries of scientific certainty. It meant questioning the absolute nature of time itself. He approached these challenges with calm reasoning, following the logic wherever it led, even when it pointed away from the comfort of established laws. He realized that time was not a universal river flowing evenly for all. It was a flexible dimension that responded to motion, stretching for some observers while compressing for others. This revelation opened a door into a new understanding of the universe, one where time and space were not rigid grids, but flexible entities influenced by movement. He also explored how energy behaved at high velocities. He observed that as objects approached the speed of light, the energy required to accelerate them grew beyond anything classical mechanics could explain. It was as though the universe placed a natural limit, preventing anything with mass from reaching light speed. He did not frame this insight as a restriction, but as a reflection of deeper harmony. The universe allowed extraordinary freedom, but within boundaries guided by symmetry and balance. These boundaries were not barriers, they were the shape of reality itself. His fascination with symmetry continued to deepen. He became convinced that the universe expressed itself through mathematical elegance. Every transformation he studied, every equation he refined, revealed delicate relationships between space, time, energy, and motion. These relationships were not accidental. They were woven into the fabric of existence, ensuring that physical laws remained consistent across all frames of reference. To him, this symmetry was the most beautiful sign that nature followed a profound internal logic. He believed that scientists were not merely observers. They were participants in a grand conversation with the cosmos. Every measurement they made altered their relationship with the universe. Every change in motion shifted their perception of reality. He imagined two observers traveling at different speeds, each experiencing time differently, each witnessing events unfold in unique sequences. And yet, both would be correct within their own frames of reference. This idea reshaped the notion of truth itself. Truth was not singular. It was relational, defined by perspective and motion. His quiet determination allowed him to push forward when others hesitated. The scientific world of his time often treated radical ideas with suspicion, preferring familiar explanations even when they contradicted evidence. But he accepted the contradictions as signs of new understanding waiting to be uncovered. He saw beauty where others saw discomfort. He saw clarity where others saw chaos. And he followed the thread of logic to its natural conclusion, revealing insights that would later become pillars of modern physics. He sensed that the universe was guiding him toward a revolution in thought, even if the full form of that revolution had not yet taken shape. He could feel it in the way his equations aligned, in the way experimental results matched his predictions, in the way inconsistencies resolved themselves once the old beliefs were set aside. He realized that the world was on the brink of seeing space and time not as separate entities, but as interconnected aspects of a unified structure. Though he did not fully articulate this union, he reached astonishingly close, unveiling the relationships that would make such a synthesis possible. He worked without seeking recognition. He understood that the pursuit of truth was larger than any individual. What mattered was not the name attached to the discovery, but the discovery itself. He trusted the future to recognize the significance of his work, even if the present could not. His role was not to demand attention, but to lay the groundwork for a transformation that would reshape humanity's understanding of reality. The world would one day look back and realize that he had perceived the future before it arrived. He had sensed the shift from absolute time to relative time, from rigid space to dynamic space, from isolated observers to interconnected frames of reference. He had carried the spark that would ignite a revolution in physics, a revolution that would forever change the way humanity sees the universe. In the end, his legacy was not measured in applause or accolades. It was measured in the silent influence that flowed through the generations of scientists who followed. His ideas became the invisible architecture of modern thought, guiding theories that pushed the boundaries of human understanding. He taught the world that the universe is not fixed but alive, not rigid but responsive, not divided but unified through the delicate interplay of motion and perception. And though history often places the spotlight on those who later expanded these ideas into complete theories, the quiet brilliance of his contributions remains woven into the very fabric of scientific progress. His work stands as a reminder that sometimes the greatest revolutions begin in silence, carried forward by those who see truth long before others are ready to understand it. When the story reaches this stage, the momentum of scientific change feels almost unstoppable. The world is standing at the edge of a new intellectual horizon, and the minds driving this transformation are working with an intensity that borders on obsession. What had once been a universe ruled by predictable mechanisms is now revealing a hidden architecture. One built not on certainty but on probability, not on rigid motion but on flickering possibilities. The journey is no longer about studying what the eye can see, it is about understanding what reality becomes when the familiar rules collapse. This era demands new thinkers, people who are not intimidated by contradictions, who embrace ambiguity as a clue rather than a barrier. And the figure at the center of this moment recognizes that the only way forward is to imagine the very structure of the atom itself. The atmosphere in laboratories and lecture halls is electric. The old guard is uneasy, sensing that the classical worldview is slipping from their grasp, while the younger generation feels something close to exhilaration. To them, the universe has begun speaking in a new voice, one that whispers in energy jumps and spectral lines. And in the middle of this scientific storm stands a man whose curiosity outweighs every difficulty. He understands that knowledge does not progress by polishing old ideas, but by replacing them with better ones. His work challenges assumptions that had been accepted for centuries, and instead of being discouraged by the resistance he faces, he takes it as a sign that he is moving in the right direction. The more he studies the behavior of electrons, the more he realizes that nature does not behave the way classical physics insists it should. Every measurement, every experiment, every anomaly points toward a strange truth: electrons do not orbit the nucleus like planets around the sun. They occupy regions of probability, they appear and vanish, they shift energy in sudden rule-bound leaps. These observations are not random. They are signatures of a deeper order that classical thinking cannot decipher. And so he begins constructing a new vision, one in which the atom is not a miniature solar system, but a complex, layered system governed by quantized energy states. This shift requires more than scientific skill, it requires philosophical courage. To accept that the universe behaves differently than intuition suggests is one of the most difficult steps a scientist can take, but he does not hesitate. Instead, he builds an entirely new conceptual language, one that allows physicists to speak about the microscopic world with accuracy instead of guesswork. This language explains why atoms glow with certain colors, why chemical elements behave uniquely, why matter is stable. The more he refines his work, the clearer it becomes that he is not merely contributing to science, he is rewriting its foundation. As his ideas spread, they ignite debates across Europe. Some physicists are stunned by their elegance, others reject them outright. The academic landscape becomes a battleground between two worldviews. On one side stands the classical tradition, proud and deeply rooted. On the other stands the emerging quantum way of thinking, bold, unsettling, and undeniably powerful. And yet, slowly but surely, the evidence begins to favor the new theory. Experiments that once puzzled researchers suddenly make perfect sense. Spectral data, previously chaotic, now fall into perfect patterns. The scientific community realizes that they are witnessing the dawn of a new era, and the man who sparked it becomes a symbol of intellectual revolution. What makes his contribution extraordinary is that he refuses to settle for half-formed ideas. He does not stop after explaining the atom's structure. He goes further, seeking to uncover the rules that govern interactions, bonds, and the behavior of entire systems. His insights begin influencing fields far beyond physics, chemistry, engineering, even philosophy. The boundaries of scientific disciplines start dissolving. Researchers from different backgrounds find themselves relying on principles born in his mind. It becomes clear that his work is not confined to laboratories. It is shaping the future of human understanding. With every new discovery, the mysteries of the universe grow more approachable. What once seemed metaphysical now appears logical. What once seemed random now carries patterns. And through all of this, his commitment remains unwavering. He continues refining formulas, questioning assumptions, and guiding younger scientists who will eventually transform his ideas into technologies that reshape the world. He understands that knowledge is not a possession, it is a responsibility. The deeper he looks into the atom, the more he realizes that uncovering truth requires humility as much as brilliance. Soon, universities across the world adopt the new atomic model he constructed. Its implications ripple outward, influencing electronics, communication, computing, and every technology built on the manipulation of energy. The theory that once seemed radical becomes the backbone of modern science. Students who had never heard of the classical model begin their education in a world where quantized energy levels are the norm. The shift is so complete that it becomes difficult to imagine a time before these concepts existed. In this transformative period, he becomes not just a researcher but a mentor, advising some of the greatest minds of the next generation. His ability to blend intuition with logic, imagination with evidence, earns him a level of respect few scientists ever achieve. His name resonates far beyond the walls of universities. He becomes a figure whose influence cannot be measured in papers or lectures, but in the collective transformation of scientific culture. As the world continues evolving, the framework he developed proves itself again and again. Every new experiment, every technological milestone, every theoretical advancement connects back to principles he uncovered. And even though he lived in a time when humanity's understanding of the universe was only beginning to expand, his vision extended far beyond his era. He saw not only what science was but what it could become. He believed that the deepest mysteries of nature were not barriers but invitations. In the end, his legacy is not limited to equations or theories. It lives in the curiosity he inspired, the boundaries he pushed, and the courage he demonstrated by challenging the assumptions of his time. He showed the world that progress demands questioning even the most sacred beliefs, that knowledge grows through risk, and that the universe rewards those who dare to look deeper. Through his work, humanity gained not just new information but a new lens, a new way of seeing reality itself. And because of that, the world would never be the same. By the time his ideas were taking shape, the scientific world had begun to sense the magnitude of the transformation underway. The quiet assumptions of centuries were giving way to something new and more intricate, a vision of the universe that demanded not only observation but imagination, not only precision but insight. He moved forward with the understanding that discovery is rarely linear. It unfolds through patterns, contradictions, and careful attention to the whispers of nature that most others overlook. He had long recognized that reality was not a rigid, unyielding stage upon which events merely played out. It was a living, dynamic system in which every measurement, every interaction, Every observer contributed to the unfolding of its laws. His work increasingly focused on the interaction between matter and energy, seeking to understand not just the structure of atoms, but the principles that govern their behavior. He realized that the microscopic world was far stranger than the visible, macroscopic one. Electrons did not simply move along fixed paths, they existed in regions of probability, manifesting patterns only when observed under specific conditions. These insights challenged everything the classical worldview had taught. Certainty gave way to probability, predictability gave way to rules of limitation and possibility. Yet, in this apparent chaos, he discovered profound order. The universe had a logic of its own, a hidden symmetry that he began to reveal through meticulous reasoning. He pondered the nature of light energy and the very forces that held atoms together. Light was no longer a simple wave, it became a messenger of quantized interactions, a signal of the deeper principles shaping matter and motion. He understood that energy could not be infinitely divided, but was packaged in discrete amounts, a realization that explained phenomena previously considered inexplicable. These quanta of energy were the building blocks of a new reality, revealing a universe that operated on rules far different from the smooth continuum assumed by classical physics. Each experiment he considered, each calculation he performed, confirmed that the atomic world was governed by these new, astonishingly precise principles. He faced resistance, as any pioneer does. Many in the scientific establishment were unwilling to abandon the comfortable certainties of Newtonian mechanics. They could not accept that nature behaved in ways that seemed paradoxical, counterintuitive, or even impossible. Yet he persisted, confident that understanding came not from conformity, but from careful attention to evidence and reason. He refined his equations, clarified his arguments, and ensured that the predictions arising from his theory could be tested. Gradually, the world began to see the elegance in his approach. What had seemed radical and implausible now appeared as the natural resolution to a series of previously unsolved mysteries. He also grasped the philosophical implications of his discoveries. Observers were no longer passive recipients of events, their measurements became part of the system itself. Reality was relational, contingent upon motion, energy, and perspective. Two observers moving differently would perceive events in unique ways, yet both perspectives were valid within the rules of the universe. He realized that this was not a limitation but a revelation. The cosmos was structured to accommodate multiple realities at once, a complex dance in which certainty existed only within defined boundaries. His work extended beyond atoms to the implications for the wider universe. The same principles that governed the smallest components of matter suggested a coherence across scales. Nature was neither random nor chaotic, but operated with consistent laws that connected the microscopic to the macroscopic. He sensed that the atomic rules he discovered were reflections of a more universal order, an underlying logic that would eventually provide a framework for understanding matter, energy, and light in ways never before imagined. Despite the challenges, he remained focused, working with a quiet intensity that few could match. Each insight, each calculation, built upon the last, forming a lattice of understanding that would later support some of the most transformative developments in modern physics. His vision was never confined to the laboratory, it extended to the very way humans perceive reality. He understood that these discoveries would reshape not only science but philosophy, technology, and the way society conceptualized the universe itself. Time, space, and energy became interwoven in his thinking. He explored how atoms absorbed and emitted energy in precise amounts, how electrons jumped between levels, and how these interactions created the phenomena of light and heat. Each observation strengthened the conviction that the universe operated on strict rules, even in domains invisible to the naked eye. His theories offered predictive power, allowing scientists to calculate outcomes with accuracy previously thought impossible. This predictive capability distinguished his work from speculation, anchoring it firmly in measurable reality. He also inspired others to think differently. Students, colleagues, and contemporaries who engaged with his ideas were challenged to reconsider their assumptions, to move beyond the comfort of established knowledge. He emphasized that curiosity, courage, and rigorous reasoning were more important than adherence to tradition. By encouraging others to question deeply and explore widely, he created a ripple effect that would extend far beyond his own lifetime. His influence became evident in the work of future scientists who built upon the principles he had laid out, shaping fields as diverse as quantum mechanics, chemistry, and nuclear physics. As his insights matured, they became a foundation for new technologies and new ways of understanding the world. The principles he discovered would later underpin innovations in electronics, energy systems, and communication technologies, demonstrating that profound scientific insights often have practical implications far beyond their initial theoretical context. He had not merely explained phenomena, he had revealed the rules by which the universe could be harnessed, predicted, and understood in increasingly sophisticated ways. Ultimately, his work revealed a universe of subtlety, beauty, and order, a universe that required a mind willing to see beyond immediate appearances. He demonstrated that discovery comes from the willingness to question, the discipline to observe, and the courage to embrace ideas that challenge common sense. Through his persistence, he showed that the most revolutionary concepts often emerge quietly in the careful synthesis of observation, reasoning, and imagination. His legacy is not measured by immediate recognition or accolades, but by the profound shift he created in the way humanity understands reality. By revealing the hidden architecture of matter, energy, and observation, he paved the way for generations of scientists to explore, experiment, and innovate. His work transformed the foundations of physics, reshaping not only science but the human conception of the universe. It stands as a testament to the power of curiosity, intellect, and the relentless pursuit of truth, demonstrating that sometimes the most significant discoveries begin in silence and grow to redefine the world.